Hey guys, in this video I'm gonna go over the analog to digital converter, and I guess I'll give you a functional description of how it works, and I'm only going to explain topics that pertain to the videos that I'm going to make on different modes that we're going to use it in. Basically I'm going to use it in single mode, where you're just doing one conversion of one channel over and over. And then the other video, the third video, is going to be on multiple channels that you're scanning over and over and getting those readings. And again, to implement just a single conversion, just one conversion, and that's it. That's easy. It's just a matter of setting or clearing one bit in the registers. Okay. So if we kind of open this up here, I wanted to just go over the main features here with you. It's a 12-bit analog to digital converter, so you get 12 bits of resolution. There's certain interrupts that we have access to, such as the end of conversion, some injected conversion and analog watchdog stuff, which I'm not going to go into. Maybe I'll go over the analog watchdog, but definitely not this, because I've never used this, so there's not much I can tell you about that. And like I just explained, there's single and continuous conversion modes. There's a scan mode, and then complementary to the scan mode, there's also discontinuous mode. Okay. There's a calibration bit that you can set to calibrate it. It does it all on its own, and that's something you have to do at every time you power up your microcontroller. And if you're going to use the ADC, you should have it calibrate. It takes a fraction of a second, so that's fine. You can have a different data alignment schemes. I leave that to default, which is right data alignment, which is how normally everything is anyways. So you can program each channel, however many channels you're using. You can program each of them to have different sampling times. Obviously, the more sampling time, the better, the more accurate the reading, but the slower it'll be. But again, when you're running in the megahertz range, you can have all the sampling time you want, and you're not going to notice so much of a difference between 100 clock cycles or 200 clock cycles, again, when you're talking about megahertz. So I usually go for more just to get better readings. There's external triggers that can trigger the readings, the conversions, but I'm not going to go over that because I don't use that. Discontinuous mode is simply that it does a reading and it stops. It'll just do one conversion and it stops, and to do it again you have to go ahead and set it yourself and do it again. Versus continuous mode, where it does one conversion after the other like that. Dual mode is when you're using both ADCs on chips that actually have two ADCs, which this one does. As you can see, the chip that I'm using, the 103, it takes 1 microsecond to do a conversion at 56 megahertz, and it takes 1.17 microseconds to do a conversion at 72 megahertz, which is what we're using it at. Or at least what I use it at. Another thing you have to keep in mind is that the voltage for the analog to digital converter has a reference of 3.6 volts. So if you're first of all, you shouldn't be putting more than that on your pins anyways. But if you're going to do a voltage reading from 0 to 5 volts on that pin, after 3.6 volts, it's just going to read the maximum number, and the rest of your voltage is meaningless. Anything above that, because it's just going to read it as 4096 or something like that. So yeah, so don't even bother with that. But again, you shouldn't even be putting any more than 3.6 volts on your inputs to your microcontroller anyways. So yeah, that's the ADC input range. DMA requests become very important when you are using scan mode, and I'll explain that to you in just a second. And that's basically what I want to explain to you from the data sheet. Oh, another thing is, I didn't mention it here, probably, I think it mentions it here, that one, it's 18 channels that are multiplexed, so that's very important to understand. And that the clock to your ADC it's coming from the APB2 bus, and it must not exceed 14 megahertz. So your ADC clock, whatever's clocking it, cannot exceed 14 megahertz. As you can see here, when your microcontroller is running at 72 megahertz, the ADCs are on the APB2 bus. Therefore, this is mostly everything is running on 72 megahertz, but the ADC cannot exceed 14 megahertz. And when your main clock is at 72, you have to use a prescaler of 6 for your ADC. 4 is too much because you're already at 18 megahertz, so that's you've already surpassed that 14. 2 obviously won't work. The very fastest you can run your ADC is at 12 megahertz. And this setting, this ADC prescaler, is in your RCC register. That is actually, if I can find it, RCC registers. I think it's in this one. Yeah, it's right there. It is right there. ADC prescaler. So you would go to this bit. Was that 1514? ADC prescaler, and as you just saw, we have to use 6. So you would go here and you do a prescaler by 6, and then your ADC would be properly properly running. All right, so now let me explain, I guess, how the ADC works. What you have is 18 channels that are multiplex. So in a multiplexing scheme, what you get is a lot of inputs, one output, and some way to select which input you want output. So if here you have channels 0 through 16, and let's say you're only using channel 5, for example, then you would go to a specific register in the ADC, which I'll show you when the time is right in the next videos when we're actually doing some code. So you go to a specific register and you tell it, hey, I'm only gonna use channel 5, and then that's the only channel it will output into its data register. And that'll work with obviously any channels. And this this is basically the scheme if you're doing just conversion for one channel, and that's it. You just put that value here and you don't have to worry about that again. However, when you're doing multiple channels, in, for example, like in scan mode, this is what happens. So here's your multiplexer, and for the sake of simplicity, let's say we only have 4 channels. Let's pretend. So channel 0 through 3. Here's your register to select. No, because I'm going to elaborate on this way to select. So there is a, if I can show that to you, there's a specific register. Where are the registers? Here they go. Sequence registers. This sequence register has some bits. These last 4 bits labeled L, which says sequence length, and then there's 16 sections of 4 bits each. Sequence 16, sequence 15, sequence 14, sequence 13, and it goes on, and it actually spans 2 more registers, and all the way until you get to sequence 1, as you can see right here. So what's going on? So let's say you're using scan mode, and or it could be discontinuous mode as well. It doesn't a discontinuous mode or continuous mode. The point is that you're scanning, that you're doing more than one channel. So let's say I'm using all of the channels. So you're gonna go to that register, and in that part that was labeled L, that had I forgot how many, I think 4 bits. You're gonna tell this, because remember, in reality we have all the way up to 16 channels. So you're gonna tell it how many channels are you sampling. All right. So in our case, for simplicity, we're gonna tell it we're only sampling 3 channels. And then you have all those other bits, sequence 16, sequence 15, all the way up to sequence 4, 3, 2, and sequence 1. Now, this is just the sequence order. So when it starts scanning, it's going to scan this one. It's going to go like this. It's going to scan this one first. Then it's going to scan sequence 2, sequence 3. That does not mean channel 1, channel 2, channel 3. No, this is just the order of the sequence. In these bits, you specify what you want to be the first in the sequence. So let's say I wanted to do channel 2 first, then you would write a 2 into those bits. If you wanted to do channel 0 next, and then channel 3, and then channel 1, if this is the order that you want, in other words, first, second, third, fourth, that's the order that you want. That's how you're going to write the bits. So don't get confused because you see sequence 1 that it's going to do channel 1 first. That's not how it works. It's the sequence. And then here you're going to tell it the length, right? So I guess in this example it would be 4. So that's where you tell it the length, so it doesn't scan all these empty non-used channels. That way it only scans channels that are actually being used. Alright, so that's how it works in scan mode. Even if you're not using scan mode, if you're only using just a single conversion of one channel, you still have to go in here, right? And actually the default is 00. This is the default. And it's actually, it's actually the number of channels that you want. Let's say if you want 4 channels, because the default is 00, which equals 1 channel. Then 001 equals 2 not channels, 2 readings, 2 conversions. 002 equals 3 conversions. Since the default 0 is equal to 1, right? 1, 2, and then basically 2, and then 3, and then 4. What am I doing? 0, 1, 2, 3. The point is that however many sequences you want, you subtract 1, right? So here's 3, and that's the number you put into here. And it does that because the first one, which is 0, doesn't mean 0 sequences. It means 1 sequence. So that's why it's kind of off by 1. Okay. So like I was saying, even if you're not using scan mode, if you're only going to do one single conversion, you still have to go in here, or you don't have to do anything because the reset is 0. So it's only going to do 1 sequence. But you're still going to have to go into sequence 1 and tell it which channel you're using, whether it's 3 or 16 or whatever. You go to sequence 1 and it tell it what channel you're going to use, even if you're only doing a single conversion. Again, if you're doing a scan conversion, then obviously you fill in all the ones that you need. And that's really the gist of it, to get these sequences right. Now what's going on? So when it does a sequence, for example, let's say it's going to do sequence 1, right? Here's the output of your conversion. It goes to the data register, and it has 16 bits here, where it gives you whatever value that is. So it'll do sequence 1, it'll let it through, it goes to the data register, then it goes to sequence 2, puts it in the data register. So basically it's overriding the previous reading. With every new reading, it overwrites the previous one. So it's very hard, and you shouldn't try to keep track of which reading it's doing, because in scan mode you're going to enable the DMA, which is the direct memory access controller, And what this is going to do is it's another peripheral in there, so we're gonna have to go into this and do some settings. But in this one, you're gonna tell it the address of this data register, right? You're gonna tell it that's gonna basically just have the address of that data register. You're gonna tell it how big this register is, so we're gonna tell it that it's 16 bits long. You're gonna tell it how many readings you want to do. You're gonna tell it, or how yeah, basically how many readings you want to do, which we're gonna do 4 for this example, right? And then you're also gonna tell it, all right, where do you want those readings to go? And in our C code, we're just gonna make an array. Let's say we're gonna call it data, and it's gonna have 4 elements, right? So then we just give it the address of this array. We give the DMA the address of this array, so we end up with data 0, data 1, 2, and 3, and it will take charge of getting sequence 1, reading the data and putting it in here in here for you. Sequence 2, it'll put it in there for you. Sequence 3, it'll put it in there for you. And sequence 4, it'll put it in there for you. That way, you don't have, since there's only one data register, you don't have to keep track of which reading it's currently doing, so you know which channel it's giving you the information for, because the DMA will do that for you, and it'll put it into a nice little array for you that you can use in your code. And that's it. And the great thing about this, there's no interrupts, there's nothing you have to do in your C code aside from the actual setting. And if you do it in continuous mode, this is always going to be happening. This DMA doesn't take any toll on the CPU or anything. You just basically, whenever you want a reading, you just go to your your array, get whatever reading you want from whatever index it's at, and that's it. So it's a very neat way this works out in scan mode. So yeah, that's really the gist of it. Obviously the ADC can do more. It has what they call the Analogue watchdog event, and that's nothing more than, let's say, here's your ADC value that it's given you, from 0 to 4095. What the Analogue watchdog does is, there's 2 registers where you give it a low value and a high value, and as your ADC is doing conversions and readings, once it passes this value, it'll give you an interrupt like, hey, we went over your high threshold. Again, when it passes this value, it's going to give you an interrupt, hey, I went over the low threshold. So if you're monitoring, let's say, a voltage or something that you don't want it to exceed or fall below a certain threshold, you can use this Analogue watchdog event. Maybe I'll implement that in a third video, but as of right now, I haven't planned on doing that. But it's pretty neat anyways. There's also something called injected channels, which I won't get into because I have no clue what they are. Also, you can have, obviously, timers can generate your conversions and different things like that. But again, that's about the gist of the ADC. And my next video, we're going to do a single conversion in continuous mode, where we're going to connect the potentiometer to the ADC and just get a reading, an analog reading, continuously. And then in the third video, I'll modify that code and we'll scan multiple channels and get multiple readings. And you'll see how we have to use the DMA controller, and it's nothing more than like 2 or 3 lines of code to get the DMA working, so don't be scared away by that. I'm not sure if I went into the calibration of the did I go into the calibration? I think I did. Either way, you'll see everything we have to do in the code, And just like with anything, it always sounds complicated, and it's really not. It's like 10 lines, no, what, one, not including the GPIO settings and RCC that we have to do for everything, probably like 3, 6, 9 lines of code to set this stuff up, which is really nothing. Alright guys, next time.